Good morning. Today we have Codeforces around Hello 2022, and we're going to try and earn red back. All right, a little late here, but let's jump right into it. A stable arrangement of rooks. We have an n by n chessboard with k rooks. Rows in this chessboard are numbered from 1 to n from top to bottom, and 1 n from left to right. The cell xy, the arrangement of rooks is called good if no rook is beaten by another rook. A good arrangement of rooks on this board is not stable if it's possible to move one rook to the adjacent cell, so this arrangement becomes not good. Please find any stable arrangement of k rooks on the n by n chessboard, or determine there is no such arrangement. But it's not stable, so you just, k has to be less than or equal to n over 2 plus 1 maybe? Yeah, okay. All right. So yeah, you can just do every other row, should be fine. Greater than or equal to n. This out, -1, continue. Otherwise, we'll do a rook only if we need one, otherwise no rook, and then like this basically. Continue, what's wrong with this? 3-2. Oh. Yeah, this math isn't right. So if n plus 1 over 2 is greater than or equal to k, or is less than k. I think that should be right. All right, looking decent. Let's move on to problem B here. Integer shop. An integer shop sells n segments. The ith of them, all right, we got it, contains all integers from Li to Ri and costs Ci coins. Tomorrow, Vasya will go to the shop, buy some segments. So, yeah, okay, we got some continuous ranges. He will get all integers that appear in at least one of the bought segments. The total cost of the purchase is the sum of the cost of all segments in it. After shopping, Vasya will gift some more integers as a gift. He will get an integer x as a gift if and only if all the conditions are satisfied. He hasn't bought it. He has bought L that's less than it, and he's bought an R greater than it. Vasya can get x as a gift only once, so we won't have the same integers after receiving the gift. Okay. Vasya buys 2, 4 for 20 coins and 7, 8. Then he gets 2, 3, 4, 7, 8. From the segments, and 5 and 6 as a gift. Due to technical issues, only the first S segments will be available tomorrow in the shop. Vasya wants to get as many integers as possible. If he can do this in different ways, he wants to select the cheapest of them. For each S from 1 to n, how many coins will Vasya spend if only the first F segments are available? How many coins will he spend? Yeah, okay. So if 1 is available, you spend just that. If 2 are available, So you always want the leftmost left endpoint and rightmost right endpoint. And then you want the cheapest of them. And then you also need the biggest thing, I think. So int n equals this, int max size equals 0, I guess. So we need print writer, which we will close at the end. All right. Then we need to handle this. So int L equals this, R equals this, cost equals this. So then we'll have a hash map integer to, I guess we'll say int leftmost equals integer.max value, L cost equals 0, int rightmost equals integer.min value, R cost equals 0. All right, max size equals max.max, R minus L plus 1, or max size. If L is less than leftmost, or L equals leftmost, and the cost is less. Then L cost equals cost, leftmost equals L. And we'll say the same thing basically with the rightmost. Then R cost equals cost, rightmost equals R. Okay. And then we'll have our answers. So I guess we just print a new line here. Wait, okay, fine. Yeah, so now int ants will be rightmost minus leftmost plus 1. So if ants equals max size, we also need max size cost. Or this equals max size and max size cost is greater than cost. Cost equals max size cost. Nope. And then max size equals R minus L plus 1. Okay, so advance equals max size, then sys out, or just out.println line, math.min of max size cost, or R cost plus L cost. Else out.println R cost plus L cost. Yep, so I think this is what we're looking for. 20, why is the second thing not 20? Okay. Yeah, it'd be 42. So rightmost is greater than 20, 42, 42, 42. Looks good. Let's move B. Let's move on to C. Interactive problem. The jury has a permutation P of length n and wants you to guess it. For this, the jury has created another permutation Q, also of length n. Initially, Q is just the same as like 1 is 1, 2 is 2, etc. You can ask queries to get Qi for any I you want, after which the jury will change, wait, what is Q? Oh, this other permutation? Okay. We'll change this other permutation in the following way. We did submit this, right? Okay, we got it. At first, the jury will create a new permutation Q prime, such that Q prime equals Q of P prime. Then the jury will replace the permutation Q with Q prime.
The answer is your problem.
Wait, what? Oh, so it shuffles everything by PI, or by P. Any paper? Sorry guys, no paper cam today. Context is too important for theatrics, you know. Okay, 4, 2, 1, 3. This is P. Okay, so initially Q equals 1, 2, 3, 4. And then, after one step, Q prime equals Q sub P prime. They're going to explain. Yes, here you go. So the first thing is what's at index 4. Wait, what? Q1 equals Q of 4. Okay, yeah. So this goes to position 4. So this is a 4. This is a 2. This goes to this position. So this is a 3, and this is a 1. Okay. So then the same thing happens again. And you get 3, 2, 4, 1. We can query any position, right? So we probably just query a cycle. Oh, wait, what? So we get any QI. Oh, we have to figure out how we're shuffling it. So the first query doesn't matter. Yeah, the first query we get no information from. All right, so yeah, you get nothing from the first step. From the second step, you get something. Let's say you query the first thing. So you know something came there. Oh, do you keep querying it until it doesn't change? Yeah. So we keep querying it until it doesn't change. So you get 4, then you get 3, and then what? So then do it again, so then we get 1, and 2 stays where it is, 3 goes here, 4 goes here. 1, 2, 3, 4. How many queries does this take? We spend 2 queries per thing. Yeah, 2 per thing. Yeah, so here we have 4. So we've got, well, initially we've got the 1. So you've got the 1, and then you've got a 4. 1, 4, 3, 1. So you've got 1. Three goes to 4. 1 goes to 3. Yeah, okay. I think this should be exactly 2n. That's a cool problem. I really like it. Very original too. Definitely worth making an interactive problem for. Okay, so Boolean array solved equals new Boolean array n. Then we'll say that equals 0 less than n plus plus. If solved at I. Continue. Otherwise, we want to say, let's find all of the things in this position. So int, I guess we need int terms used equals 0. Okay, so then this is out.println. Is this out I plus 1? But a question mark. So question mark I plus 1, get the next thing, subtract 1. Check if it's in the cycle. Okay. Then we need, so we get the cycle, now we need to solve this cycle. So each thing goes to the next thing in the cycle. Yeah. So int start. Oh, yeah, so for int offset equals 0, offset is less than in cycle that's size, offset plus plus. Good. Then we'll say int current equals in cycle that get turns use plus plus. Modulo in cycle dot size. Yeah, okay, so we got this current, and next will be almost the same thing. This plus 1. And then we need our answer. So ants at current equals next. So 4. What? Oh, it's a multi-test case. Okay, 4. 1 is initially a 1, and then a 4, and then a 3, and then a 1. Shouldn't be 1 anymore. Oh. Oh, dang it. Okay, then 4. And I in cycle solve that I is true. Okay, one test case, n equals 4, you get 1, then 4, then 3, oops, then 1, 3, we'll keep it 3. I think this should be right.
Well done, sir. Facing on problem C.
Okay. Solid. Let's move on. Kobe. Sorry. Rip. Rest in peace, Kobe. Didn't mean to be inappropriate there. Not stomping on any graves. I know I used him in my recent YouTube video, so he's a good guy. Lots of talent. All right, circular land is I mean it purely in respectful term, honoring his skill, you know. Circular land is a 2n by 2n grid. Rows of this grid are numbered by integers from 1 to 2n. Okay, is this really necessary? Can this just like be implied? There are, or like, can we put like a horizontal line or something under this so we know where to start reading the problems? There are n squared of your friends on the top left corner of the grid. Wait. There are n squared of your friends in the top left corner of the grid. Oh, okay. So you've got a grid, some of them are full. Okay. Your friends want to get to the bottom right corner of the grid. For this, in each cell, there should be exactly one friend. Gotcha. You want to decide to help your friends to get to the bottom right corner of the grid. You can give instructions of the following type. Select a row. All friends should move to the next cell in the row. So all friends move right. Oh, yeah, all friends move because they do yx. Yeah, okay. Select a row. All friends should move left. Okay. Select a column. All friends move down or all friends move up. Yep. You can give such instructions any number of times. You can give instructions of different types. After any one instruction, if after any instruction one of your friends is in the cell covered with snow, he becomes ill. There are snow cells. Oh, some of the cells are covered with snow. I just totally missed that. Okay. In order to save your friends, you can remove snow from some cells before giving the first instruction. You can, so we're gonna have to remove at least one of them, or we might have to. You want to spend the minimum number of coins and give some instructions to your friends. After this, all of your friends should be in the bottom right corner of the grid and none of them should be ill. Please find how many coins you will spend. So we definitely need to clear out the top left. Well, okay, so yeah, top left and the bottom right 100% need to be clear. So this is safe. And this will also be safe, the top left. I think you just need any path, right? What is this input? Is the number of, oh, the cost of removing snow from cells. So surely this is just 4 plus 18. The second one is 4 plus 18, what, 22? Yeah. Is it really just clear out any path? So this one, is this one just going to be 2 plus 8 plus 4 is 14? Okay. Is this one 42? Ah, so annoying. 2 times 3 plus 10 plus 8, 10, 17 plus 7, 40, 42. Okay, there's no way this problem gets approved if it's this dumb, right? Oh wait, is it any path? Ah, wait, any path? Can you use a path? That's a good question. Yeah, so it could be just a direct over and down, but it seems like that's not necessarily the case. Real question is like, how many people are getting this wrong here? 2 submits. Okay, so more than 2 submits. Plus 93 is exactly what I need to be GM. Okay, lots of people are getting it wrong. Are people I know getting it wrong? Or just random strangers? 5 demands. I just spelled safe, S-A-F-F. Forgot to put the second line or the third line on the E. Okay. Dang it. Sorry about this camera, guys. Give me a minute. A little bit better. It's also like very low. All right. Yeah, so I have no idea how long that was broken for him. Anyway, so we can have some path. Maybe we go like right, up, left. Wait, what if there are friends? Oh, they cycle. Oh. It's cyclic. Wait, that's why. Wait, so this isn't necessary. Why is this 42? This shouldn't be 42. It should be just 40. Bring up the calculator. Okay, yeah, it's just 40. So the question is like, oh, maybe you fill in this top row last? Yeah, so if they're all going to be in this group, is there always going to be at least one column they don't use? Yeah, you never, like, it doesn't make sense to use every column in the top. Like, yeah, so it's always possible. So there's always a column you don't use. You can just move everyone down. Okay, so it's, so we've got a BF, or a Dijkstra's problem. That is another good problem. I like it, I like it. So we have like the start, we have the end, and then we have every other node's entrance and exit. Yeah. It's a directed graph. All right, how many nodes do we have? 250 times 2 squared times 4. 500 squared is not that big. Yeah. All right. C, D. Okay, then we need int double array grid, new int array n by n, or 2n by 2n. Okay, so then for int I equals 0, I less than n x plus, j equals 0, j is less than n, j plus, we'll have a long answer equals 0, ans plus equals grid at n plus I, and n plus j. So we remove everything, and then static class node. Well, we don't really need this, do we? Yeah, we do. Static class edge. And then static class state. So So node at, and then long cost, public state. Node at, long cost. This dot at equals at, this dot cost equals cost. Return long dot compare cost o dot cost. All right, so this has a node 2 long cost. And then this has an array list of node adjacencies, new array lists. Yeah. Okay. So we have node double array entrances equals new node n times 2 by n times 2. Yep. And I equals 0, and then also exits. All right, then for int I equals 0, less than n. For int j equals 0, j is less than n, j plus plus. Node new entrance equals new node. Oops, and then new exit equals new node. Entrances at, oh, we have to do this twice. Okay. Yeah, okay. So, I guess we also need long dist. Entrances at n plus I by j equals new entrance. Exits. Okay, and then we have the opposite, like this one here. Oh, these are 2. Yeah, okay. All right, so we build most of them. So now we need a node start equals new node. Yeah, and then node ends equals new node. Okay, so for node, or for int I equals 0, I is less than n, I plus plus, and then j equals 0, j is less than n, j plus plus. Entrances at ij equals exits at ij equals start. Oops, okay. And n plus I to n plus j, the same thing. This equals the end. Yeah, so we should be good there. Dist equals -1, or I guess long dot max value. So start dot dist equals 0. Okay. Then for int I equals 0 less than 2 times n, I plus plus, and j equals 0 is less than 2 times n, j plus plus. D equals 0, d is less than 4, d plus plus. -1, 1, 0, 0. That's their changes in x. We also need changes in y. Okay, so now we need int nx equals I plus dx at d, and y equals j plus dy at d if nx is less than 0, or ny is less than 0, or nx greater than or equal to 2 times x, or ny is greater than or equal to 2 times x, then continue. All right, otherwise we need to 2 times n, excuse me. Then we need to add some edges. So if exits at ij is equal to entrances at nx and y, then continue, because we don't actually need to go to ourself. Oh, we also need us to ourself. Yeah, so, okay. If entrances at ij is not equal to exits at ij, oh, so where's, yeah, so we do this, and then we need to say this equals 0. So we don't want to pay for it again. Okay, so now entrances at ij dot adjacency edge dot add new edge to exits at ij, and then the cost will be grid at ij. Yep. Okay, we still have to do Dijkstra's at the end. But before that, we do this part. Well, so this is the new x, new y. We handle that. Yes, otherwise add an edge. So now we have exits at ij dot add adjacency dot add new edge to entrances at nx and y. Cost is 0. Okay. Now we need a priority. Q state, oh hello, state PQ, new priority Q. And now how do we handle this? So we need to say PQ.add start dot dist equals 0. Oh, add new state start 0. And while not PQ dot is empty, state next equals PQ dot remove. If next dot cost is not equal to next dot at dot dist, then continue. Otherwise, for node n or for edge e in next dot at dot adjacency. So long next cost will be e dot cost plus next dot cost. If next cost is less than e dot cost, then e dot cost equals next cost, and then we need to add to the priority queue. So pq dot add new state e next cost. Oh, e dot 2 next cost. All right, so we have this done, and now the answer should just be, yeah. So now we just say ans plus equals end dot dist. This out the answer. Dang it. So this means this isn't working somehow. So are we actually adding these edges? Looks right. Yeah, let's just look at the first test case, I guess. Nice and simple. Don't add any edges. Oh. from 0, 0 to 1, 0, from 0, 0 to 0, 1. Okay. Oh, less cost e dot 2 this. Oh, really? So we do hit something. We hit 3 things? That's kind of weird. Oh, this isn't right. So this is n plus n, and this is plus n. So 0, 0, 0, 1, 1, 0. Shouldn't be taking this long. Oh. E dot cost equals, no, this is E dot 2 dot this. Yeah, okay. Can't write Dijkstra's. $44. Oh, yeah. So this isn't true. Nx equals nx plus 2 times n modulo 2 times n. Thanks for the sample.
answer.
Really? That's annoying. Is it an idea thing? Is it an idea thing? Maybe it's an idea. So if we have like a 3 by 3, okay, so let's say you can go here, here, here. So we go over, over. Oh, we have a problem. Yeah, this doesn't work. Yeah, interesting. So I guess let's break it. Let's just use 9. Yeah. So if we make this 0, this 0, and this 0. In this case, I'm saying this is possible. I don't think this is possible. Yeah. The answer shouldn't actually be 0 here. So you can take the top for free, or you can take the bottom for free. These are free. You also need I guess the same problem happens in reverse. You need like one place to store these things, at least. Like somewhere. That's hard. Okay, let's read E instead. It's very hard. You decided to open a new school. We found N teachers and M groups of students. The ith group consists of K greater than or equal to 2 students. You know the age of each teacher and each student. The ages of teachers A1 to AN and the ages of the teachers are A1 to AN. Oh, because we have N teachers. The ages of the students in the ith group are B1 to BK. Can a student be in multiple groups? Okay, we don't know. To start the lessons, we should assign the teacher to each group of students. Okay. Such an assignment should satisfy the following requirements. Each group, exactly one teacher is assigned. Each teacher, at most one group of students is assigned. Okay, yeah, sure. The average of the students' ages in the group does not exceed the age of the teacher assigned to the group. Okay. So this seems pretty easy so far, but it's going to get harder. Recently, you have heard that one of the students will refuse to study in your school. After this, the size of one group will decrease by 1, while all other groups will remain unchanged. You don't know who will refuse to study. For each student, determine if you can start the lessons in the case of his refusal. Got it. Yeah, okay. So the naive is like just solve this several times. So we just have like a bunch of values. Yeah, we just like sort the teachers. And then we sort the classes. Sort the teachers, sort the classes. We want both to be sorted. Ah, look at this. So you want to know why the camera died? Because it wasn't plugged in. Who would have thought? Oh, connecting to USB mass storage. Try again. Why are we connecting to USB mass storage? Stop. I don't want mass storage. Alright, I guess we're just going to have to deal with it. Maybe. There we go. Okay, should be better. Hopefully. I guess we'll see. Back to the contest. Yeah, so we sort and then just see is everything in AI less than BI? Oh, so I think this is just like pretty easy, right? So like we change one number, essentially. Change one number. And then we want to see, is this still true? So we just need like, these things will stay the same. These things at the end will stay the same. Then we have a big group of things on one side that gets moved over one, like left one. They're all moved left one. And then we have one thing that gets moved to the right side here. Yeah, it's easy. Easy. Okay. So we just need like a tree mat. We're gonna need a couple things. We need a tree mat. Is this worth like significantly more points? Really, it is. That's kind of surprising because it's not hard. Like it's not no harder. It's gonna take a minute to code, but yeah. Dang it! I'm gonna lose so much rating on not solving D. But we might as well just get E now that we know how to. So yeah, so we need a tree map. We need some bits. And that's it. Yeah, okay. All right, so static class group. Wait, can the students can they be equal? Doesn't exceed, yeah. Oh, so we want like students average sealed, actually. And then inter values, so new inter group. Oh, okay, whatever this is. And then we also probably need int position public group. Right, and then average sealed equals sum plus n minus 1 over n. Okay, implements comparable group. Okay, public int compare to group O, return integer dot compare. Good. So we have, oh wait, it's not n and n. All right, but we only use the best n teachers still anyway, right? Each group is assigned exactly one teacher. Each teacher, at most, one group of students. Yeah, so we only use the best n of them. The number of teachers and the number of groups, yeah. Okay, int, oh, hello, int n teachers, n groups equals this. B at I equals teachers raw. Oh, we need to sort this. Sort teachers raw. Okay, so B at I equals teachers raw at n groups. Oh, at okay. I plus n teachers minus n groups. Okay, then this will be sorted still, which is convenient. Now we need our group array. So group array A equals new group array and groups. How does this input work? We have the number of teachers, 2m. So this is the number of students in each group. Oh, so we have the size and then what they are. Okay. Int n equals this. Int array values equals read array size n. A at I equals new group values. Group, so A at I dot position equals I. Yeah, all right. So then I guess we need like some sort of tree set here, right? So tree map integer. Well, okay, let's handle that in a bit. No pun intended. Please don't two-factor authentication me, GitHub. Oh no, you're not. God. I'm sure one of my subscribers works for Microsoft. You gotta tell them this is just obnoxious. Like, chill with this. This is like, I've probably done two-factor authentication on this computer like at least 5 times. They gotta ease up a bit. This is like seriously annoying. Nope, I don't want the package statement. Okay, we got the bit. So bit array, okay, to stay. Oh. Okay, left, and then okay, right. So if A at I dot average, come on, if this is greater than or equal to B at I, then okay to stay dot update I by 1. Okay, so we do this, yeah. So if I is greater than or equal to 0, or greater than 0, and A at I dot average sealed is greater than or equal to B at I minus 1, then okay left dot add or dot update I by 1, and then if I plus 1 is less than n, groups, plus 1, update on that one. This is okay, right? All right, so we've got the bits. What are we doing for this? We print a string of zeros and ones. Okay. Oh, we need the original groups. Yeah, we need the original groups still. Yeah, okay, so now we have the unsorted one. Okay, so now we need the sum as well. Yeah. All right, so now we need to consider changing a group value. So group old value well, I guess so it doesn't really matter which index we move it to. Yeah, it does. Kinda. Okay, so yeah, let's build this tree set here. Tree set, integer, last thing with average. Tree map. So yeah, last thing with average dot put I dot average sealed position I. Okay. So group old value int decrease sum or int change sum by I guess this is just decrease sum by. So we said we remove a person. Okay, so we have the old value, we have the amount we decrease the sum by, we need this tree map. What else do we want here? We also need these bits. Okay, so if dex sum by equals old value dot average sealed, then return okay I guess we also want int n groups. Yeah. All right, so then return OK left, or OK to stay dot query from 0 n groups minus 1 equals n groups. So here's nothing changes. If dec sum by greater than old value dot average sealed, then this okay, yeah, then what happens? So then this moves, so we decrease it by a big amount, so it moves left. All right. Old value dot sum minus old value, or minus dec sum by plus old value dot n minus 1 or minus 2 over old value dot n minus 1. This is our new average. What do we do with this, though? All right, so we have int old index will be old value dot position. Int new index will be oh wait, this is, let's do the one where it moves right first. So yeah, we're going to push something else to the right. So this is going to be last thing with average dot higher entry of new average. Okay, so this is, I guess, entry. What position will this be? This will be position n. So this is the new index, okay? So int n good will be okay to stay that query from 0 to old index minus 1 plus okay to stay that query from new index plus 1 to n groups plus okay left that query from old index plus 1 to new index. And then if new average is greater than or equal to, oh, we also need B. B at new index, then nGood plus plus, return nGood equals ngroups. All right, so we've got that. Otherwise, it's moving left. So int old index equals old value dot position. Well, yeah, let's call it old index. Int new index will be something else. So the thing less than this, yeah. This will be position minus 1. Dot lower entry, get value plus 1. All right, int nGood will be okay to stay dot query from 0 to new index minus 1. Plus okay to stay dot query from old index plus 1 to ngroups minus 1. Plus okay, so each of these things go right dot query from new index to old index minus 1. And then if new average is greater than or equal to b at new index, then nGood plus plus. I think that's right. Oh, we also have this thing. So if R is greater, or if L left is greater than right, return 0. That should really just be part of it in general. Okay. All right, then for group G in unsorted. For int I in G dot values, if so group G, removed by I, last thing with average, okay to stay, okay left, okay right, and groups B. Darn it. Why? All right, so we have 1 and 1. Just these two, right? Okay, 0, 1, 0. If we can remove it. Okay. So if you remove 25, the average of 16 and 37 is 27. Is that true? 16 plus 37 or 2. What? 16 plus 37 so it is 27, yeah. Wait, what do we print? Greater than or equal, it should be less than or equal to. Yeah.
Problem, you got wrong answer. Test 14, sir.
Test 14. The idea is almost certainly right. Can the bits shouldn't overflow because it's just ones or zeros. So what can overflow? Oof, annoying. Okay. It's multi-test case too, isn't it? Yeah, it's multi-test case. How does it get wrong? You answer test 14. Okay. So this is like, should be an integer, that's fine. Oh, wait. Lower entry. Yeah, what can overflow here? So we can't hit OK left at 0 ever. All the next +1 and OK right at all the next -1. This new average is a bit tricky. Okay, yeah, this is a linear number of things. Linear number of things. Max value in groups. This shouldn't be wrong. This should be right. Why is it wrong? Stay, left, right, and groups B. Is B sorted? Sorted teachers raw, and then I copy it in order. Do we want to be sealing the averages? Yeah. Okay, guess let's try a dumb case. So one test case. Oh, nothing is static, right? Yeah. So one test case, we'll have 5 teachers, one group. We'll have 2 students. Oh, let's have this one group is 2 students, which are 3 and 3. They're both possible. Should be possible again. I have no idea why this is wrong. No idea. Okay. This should be fine. I guess we can make this a long. No idea what could possibly be wrong here. So this should definitely just be the same, should just be equivalent. No. Okay, let's double read the problem. The ages of teachers are A1 to A, and the ages of students in the ith group are B1 to BK. To start lessons, we should assign the teacher to each group of students. Such assignment should satisfy the following requirement. Each group should have exactly one teacher. To each teacher, at most one group of students should be assigned. Okay. The average of the students' ages in the group does not exceed the age of the teacher of that group. So the teacher is bigger or they're the same. One of the students will leave. Sum is along though. Yeah. Okay, minus equals. What the heck? How? Is this not how you do it naively? Sort both, assign the best teachers to each group of students? If the best group of students needs to have a teacher, it's the best one, so we might as well give them the best teacher. Okay, then the next best gets the next best teacher. Yeah. So it's just sort them and then give, yeah. What the heck? Is my sort method wrong? No. This should be 0, 0, 1, 1. Oh. So this should be 0, 1, 0, 1. That's not right. Oh wait, it is right. Yeah, you need to remove the 5. Do we write a brute force for this? So in M equals 1 plus random. Teachers is less than n groups. Then okay, so iterate teachers equals get random array. I guess we'll say 1 plus. Get random array size and teachers. Oh, print the size. This looks right. All right, so then we need brute force. This stuff we don't need. Well, maybe we do need that, but oh well. So yeah, for group G in unsorted, n dot equals 0, I is less than G dot n plus. Int old val equals G dot values at G dot I. Where old values equals G values at I. Okay, so then the new sum will be G dot, how much time? G dot n minus 2 over G dot n minus 1. Greater than A dot average sealed is greater than teachers at J. J minus n teachers plus n groups. Oh, plus n teachers minus n groups. Then this out 0. Continue outer this out. This looks different. 3, 4, 5. Okay. are back in the races with 14 minutes left. Okay, so we have 2 teachers that are 2 and 2. All right, then we have one group that is 1, 3, 2, and another group that is, so the average of this is 2. The other group is 2, 2, 1. Dang it. Brute force is wrong. Oh. Wait, that's not right. Yeah, none of this is right. the heck? Why is this so hard? Okay. One test case. Good Lord. Okay, so test case 441. Seven minutes. Oh my goodness. Okay. Three, 4, 5. We have 4 groups. So we have 3, 5. We have this is 100% wrong. 2, 2, 3, 1, 3, 1. 5, 3. And then 2, 1, 2. So we only care about 3, 3, 4, 5 of the teachers. So it's these 2 ones. So this one goes to 4. This one also goes to 4. This one goes to 2. looking right. Okay. Plus old index plus new index. So this is 2. This is 4. This is 2. Next 0. Oh, we need the first thing. Okay. It was this. Come on, let me submit. Let me submit. Let me submit. Yeah, it increases. This will always exist. Oh, I should probably. Okay. All right. Do we have time to? No. Get D. Dang it. Really? I guess let's try D. Okay. Yeah, is there an easy way of doing D? Man, what? This frame rate is horrendous. So I don't necessarily need any of these things. You can take one of these if you want. Oh, is it just this? Oh my goodness, is it that easy? This. Oh no. Is it that easy? It's that easy, isn't it? No. No. No, it's so easy. Oh no. I'm killing myself here. Not literally, but this is this is a banger. This is such an easy problem. Did I get a plus 93? Or I'm at like plus 92 here. Oh, come on, guys. What do I have? Do I get red back here? Do I get red back? So it said plus, I think plus 93 is exactly what I need. Yeah, I need exactly plus 93 to re-earn my red back. Oh my goodness. Oh my goodness. Can you imagine? You know what would be absolutely hilarious? If the so if this hasn't updated yet and I get plus 92, but the reason that I get plus 92 was because I was like 10 seconds late because I had the two-factor authentication thing for GitHub. So I lost like a couple points on this and a couple points on like ABC. That would be comical. Can you imagine? Can you imagine? Look, it's a 1 point difference. This is a 2 point difference. Yeah, if I only need one more point, a couple places might be the. Oh, that would be so funny. That would be okay. We'll have solutions here. Yeah. Dang. Okay. Oh, I don't get plus 93. I get minus 30. Yeah. Well, that makes much more sense because it's a bad performance. Yeah. Plus 93 is what's needed for the next one. Yeah, I was like, for 650th place, that's quite bad. Okay, okay. Oh, and then green is if you got it. Yeah, so I think for D you only need, second page again. I think for D you only need like, to check some very simple things. Oh, maybe also these. This. Yeah. Yeah, D is easy. D is one of the easiest problems ever. Tourist got this in 6 minutes. So fast. Actually insane. Okay. Yeah, I guess we can talk about solutions then. Sure. So, here we go. So yeah, I'll have solutions to A through E, because I think I just figured out D. Yeah, so A is pretty easy. The idea is you have some grid, and you need to place some rooks on it. And let's just do it like a 5 by 5 here. So if we need a bunch of rooks to not attack each other, we might as well just put the rooks along the diagonal, since the chessboard's a square. This is 5 by 5. So we have something like this. This is one way of doing it. The problem is this isn't stable because you can move a rook over by 1 and then it can attack another rook. So we have to get rid of this rook and this rook. This gives us like the best stable configuration. In particular for n rows, then you can get n plus 1 over 2 rooks. Or like, in other words, this is like floor of n over 2, or sorry, ceiling of n over 2 rooks. And you just place them along the diagonal. So yeah, you can do this. Obviously, if you need to place fewer rooks, then you just delete some of these, and then you're good. So yeah, here's the implementation for that. Pretty simple. That's the idea for problem A. All right, on to problem B. Integer shop. Okay, integer cells, n segments. Yeah. So what happens for B is you've got a bunch of segments for sale. And maybe you've got like this segment here. Maybe you've got this segment here. And then maybe you have like this segment. So if you buy some segments, maybe you buy, like, let's say you buy just the first and the last, then you'll get all like integers in the first segment, all integers in the last segment, but you also get anything that's like between two segments that you have. So for free, you would get all of these, and then you would at the end you'd have this entire range. So all that matters is like your leftmost left endpoint and your rightmost right endpoint. And with that information, you can tell how many integers you'll have in total. So you need to buy whatever range has the leftmost left endpoint. or at least one of them if there are several. You also need to buy at least one of the ranges that has the rightmost right endpoint. And for everything, like everything else, you don't need to worry about buying it because you'll have all integers you could possibly have. So you probably want to buy the cheapest one with the leftmost left endpoint, and the cheapest one with the rightmost right endpoint. But you might not. There's one exception, which is it's possible you only need to buy one range rather than two. So if that's the case, you have to consider buying the left and the right, but you also might just buy just that full range if that's cheaper. And you can only do that if there's one range which covers literally all of the numbers you could get. So you can keep track of three things: the size of like the answer, or the size of like the biggest range that you can buy alone, the cost of whatever that range is, like the minimum cost of the maximal range, the leftmost thing, and then the best cost for it, and the rightmost thing and the best cost for it. And then you just maintain all of those, and then you have to, this is the case that I talked about, but otherwise it's just the sum of the two costs. So yeah, that's the idea for problem B. Okay, on to C. Hidden permutations, interactive. Yeah, so this is a cool problem. So let's talk about I guess what happens here. So you've got some hidden permutation. Their example was 4, 2, 1, 3. Initially, there's a separate permutation, which just starts as 1, 2, 3, 4, and then a bunch of steps happen. So after each step, this 4, or the thing in this position, will move to where the 4 is. So the thing in position 4 goes here. The thing that used to be in position 2 goes here. The thing that used to be in position 1 goes here, and 3 goes here. So after one step, their permutation will look like this. It'll have 4, 2, 1, 3. I guess it'll just be the same as this. After a second step, we move the 3 to the beginning, so there's a 3 here. The 2 stays where it is again. And then the thing here is the thing that used to be in position 1, so this is a 1. And this would be the 4. That's not right. This is the 4. Yeah, the thing that used to be in position 1 goes here. And then the thing that used to be in position 3 goes here, so this is a 1. And then if we do this one more time, we'll get back to 1, 2, 3, 4. There's a thing that used to be in position 4 goes to the beginning. That's the 1. 2 stays where it is, etc. Okay, so yeah, each step you get the next version of this permutation, then it'll cycle. But the question is, you get to ask a bunch of queries, and each one is like your first query is after step 1, second query is after step 2, and so on. So you can ask for any element in this array here. So you might ask for the first element, and you'll get this 1, but you don't get to know what the rest of these are. And then the second turn, maybe you ask for the third element, you get the 1 again. The next turn, maybe you ask for the fourth element, you get the 1. Now here we can see the path the 1 takes. So if we can see like the cycle that the 1 takes, that obviously solved the problem. But the issue is we don't really know where to query because the 1 moved somewhere and we're not sure where it went. So it's very tricky for us to do that. Instead, a better approach is we can just keep querying the same thing, and we know the things will cycle back to this position. So if we query this part, we can get this 1, the 4, the 3, and the 1. And we know there's a cycle here. So we know the first thing here is a 1, the next thing's a 4, and then a 3, and then back to 1. Which means the thing that moves here is the 4. So we have this 1, then we have this 4. So the thing in position 1 is a 4. We know that. After the 4, we have a 3, which means the thing that moves to position 4 on that first turn was from position 3. So that means this number is a 3. So we figured out this, and then we figured out this. And finally, we know the next thing is a 1, which means the thing that moved to position 3 was a 1, because then it went to position 4, then back. So we know this thing here is a 1. So we can figure out these 3 elements by seeing this cycle. So in other words, if we look at n steps, if we have an n-step cycle, we can figure that out in n+1 queries. Because we see this thing, and then we see it a second time, and everything else we see once. Worst case is that we just have the identity permutation, which is what we have to solve. And in that case, we have, what, exactly 2 times n queries is our worst case. So that's good enough for the problem. But I guess just to finish what I was talking about here, once we've found these three by finding this first cycle, then we'll move on to the next number which we haven't solved, and then keep querying that till we find a cycle. So yeah, that's the idea. And that'll give us all of these. Awesome. That's the idea to problem C. Hopefully that made sense. I guess I'll scroll through what we do here. So here's the answer. Here are which positions we have solved. And then here's how many turns we've used. You have to account for that a little bit, but you can also just say the thing which is at this right position is where it started. So you don't actually need to keep track of this if you don't want to. But yeah, so then we have a list of what happens in the cycle, and then also I do a hash set so that I don't have to make this n squared. But you probably don't need that, at least in C++, because bounds are small. And then, yeah, you do some stuff. So you just keep querying until you find a cycle, and then once you do, you mark everything as solved, and then fill in your permutation, and then print it at the end. That's the idea. Okay, let's talk about problem D. The winter hike. Yeah, so this is, oof. I choked on this one. I started implementing a solution which is totally wrong. Okay, so the idea is you have this big grid. We'll do a 3x3. So initially in these top left positions, you've got, yeah, this top left 3x3 here, which is all zeros. In this example, you have a bunch of friends that start here, and then they have to reach the bottom right 3x3. And what you can do is some operations where you pick a row or a column and then shift everything cyclically. So we could like take this row here, shift everything one to the right, and it wraps around. So the rightmost thing goes back to the beginning. The problem is some of your friends might step in snow. So that's not allowed. You have to clear off all of the snow places that you might need to before you start. Okay, so you want to get everybody from the top left to the bottom right, and you want to know what's the total like snow that you have to clear. If there's a number here, you have to pay that much in order to clear the space. So obviously, since everyone has to end in the bottom right, you got to clear all that out. All right, so that's pretty easy. You might as well just do that anyway. Then after that, the question is like, well, how do you do it? So you might be able to just like, you can delete like this one here, and then everyone can go through this corner here. So maybe you can just delete this corner, but it's possible this corner is really expensive. So maybe you don't want to delete the corner. What if you have like some path here? So in this example, you could like maybe move some people over here, like take these three, move them to the right. Then they're taking these three positions, then move them to the right again. They have these three. And then you can shuffle this guy down into your answer. And you manage to get this entire row all over to the end in just a couple moves. So it's pretty easy, right? So it's like maybe this is something you want to do. Turns out that's never the case. So the reason why is that you still have these three positions and these three positions that are open, right? And if you're going to use this path, you have to like shift one of these rows up or down. Like there's no other way of doing it. So if you're going to shift one of these rows up or down, that means either this position here or this position here are going to be like, you're going to hit them, right? Because if you shift this up to move this guy here, then that means this one is going to hit this position here. So one of these positions is going to get hit, which means it doesn't make sense for you to pay for all of these things, because if you do clear out this space, I'll just put a T here or whatever. If you clear out this space, or okay, yeah, you're going to clear out this space anyway, then you can just, everyone can just like shuffle in this way, right? So it turns out if you're going from this top left here to the bottom right here, the spaces you need to check are this, 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 and then this, 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 this. You're going to have to clear one of the x's, and if you do clear one of the x's, that's all you need, right? So you might as well just do that. So it's just the sum of the things in the bottom right plus the min of these 8 spaces. If n is 1, they overlap, but it's, I mean, still easy because when n is 1, you have to do it anyway. And when n is 2, like it's the same thing as well. So yeah, that's the solution. Somehow I did not see this. I thought you could do any path, which isn't the case. So this is really easy to implement, but you just have to, I guess, see it. Okay, problem E. This is the last one that I read, unfortunately. Yeah, how do you do it? New school. So you have a school with some teachers and some groups, and you're gonna have one student get kicked out. You don't know which student, so you're gonna try it for every student. And the question is, for each student, if he gets kicked out, can you give a teacher to each group so that the teacher is older than the average student age in the group? Or the teacher is the same age as the average, where the average can be a double, so you have to be careful there. So yeah, let's talk about that. Let's talk about what it would be like if we didn't have a student leaving, right? So let's say we just have some teachers. Maybe the teachers have these strengths, and we have some groups where the average is maybe like 3.2, or let's say 2.3, 3.2, let's say 3.4, and then 5. Maybe these are the averages. So I took the liberty of sorting these, but it should be pretty clear that if we have both of these sorted, that's probably helpful. Now, the first thing is, like, let's say this is a teacher of age 2. There's no reason, if we've got 3 groups here, there's no reason for us to use anything but the oldest 3 teachers, right? We can use an exchange argument. A teacher is more versatile if he's older. So we might as well just pick the oldest teachers, and then we can just get rid of the earlier ones because we don't care about them anyway. So now we have n teachers and n groups. The oldest group is like the most constraining. So we might as well try to assign the oldest group to the oldest teacher. And then we'll just keep doing that. So in other words, we want to sort the teachers and sort the groups, and then check if at every position the teacher is at least as old as the average of the student groups. Obviously, all that matters in the group of students is the average. That's it. So yeah, that's the idea. We just want to do that. Now, back to the original problem, the only difference between that and this problem is that here we're changing one of the values. So we've got like these values here and these values here, and then we're like, okay, take these values, except change this average to a different number. That's the only difference. Now, there are a bit more constraints on how it's changed, but in practice it doesn't really matter too much because we can solve this problem if it were changed arbitrarily. So yeah, what does this mean? Basically, this bottom array is going to change in some way. We're going to remove one element here. We're going to move it somewhere else, maybe change to like 5.4 or something. And then we want to see, is this possible still? And in this case, it's not because these mismatch. But to evaluate it, what we can do is like we have a bunch of these initial positions and then a bunch of like the final positions. And we know we're going to have like some continuous range here that gets moved either one left or one right. So we just need to know for everything in the initial array, I guess all of the things on the bottom here, can they get moved one left? Can they get moved one right? And are they safe where they are now? And if we know that for everything, we know when we change the bottom array, it's going to change in a very predictable way. You'll have a group in the front that stays where it is, a group in the end that stays where it is, and then you'll have like one group that gets moved a lot, or one element that gets moved a lot, and then one continuous group that gets moved, everything gets shifted by 1. So yeah, that's the idea. So like this group here will get shifted right 1. So we'll like take this here, it'll get moved over here. This thing stayed where it was, this thing stayed where it was, this moved by a bunch. So we'll have to recheck this versus this. But then for these 3 things that all got moved to the right one, we just check, can each of these things get moved to the right one? And we can do that using a Fenwick tree or a segment tree or a whole bunch of things. So yeah, that's the idea for the solution. We just do this in log time per person. And that's the idea. So I can show you the code for that. It's a little annoying because you're moving things around. You need to keep a copy of the original, but I guess that's fine. So we have each of the teachers sorted, and then I put the teachers in this B array, which is just, I only look at the oldest teachers. The rest of them I just throw away. Then I have this A array, which is some groups. And these are going to be sorted, but I also keep an unsorted copy to answer my queries. So I read in all the values, handle it, blah, blah, blah. Yep. And then I have these 3 Fenwick trees. So this one says, like, is the group at this position okay if we leave it where it is? Will it still be younger than its teacher? Then this is like, if we move this group left by 1, will it be younger than its teacher? And then if we move this group right by 1, will it be younger than its teacher? And then I fill all those in. Those are very easy to calculate. And then this part's a little annoying. So this is to calculate, this is the part that I had a bug in earlier. If you move something, or this is like, yeah, if you change something's value, this tree map tells you where does it end up. That's what I'm using it for. So I store the last thing with each average in this array. And I'm going to say, like, if I remove it from this and put it somewhere else, like, what does it end up being? So yeah, that's what is happening here. And then I pad it with these for when I use it. Okay, so then to actually answer a query, I just say, like, if you have this group and you decrease the sum by this, but also remove a person, is it still okay? Okay, so we got some debug here. I'll get rid of this to make it more pretty. So I calculate the new average for this group. If it stays the same, we just want to say, then the array is not going to change. So I say, can everybody be okay with what they're at? And if so, it's good, otherwise it's bad. Otherwise, they're either going to move left or right. So if they're moving left, I find their new position. So this is, you got to be very careful with this. So if it's moving left, I find the last thing, like the first thing less than it, I'm going to be to the right of that. So since this is the last thing in the array with the average, I need to go less than it, and I'm to its right. When I'm moving right, I need the last thing with this average or more, and that will be my new position, and everything else will get moved left to fill my gap. So yeah, these are slightly asymmetric, which I guess you're used to if you do C++ stuff. Or you should be used to if you're any good at competitive programming, but I wasn't used to it. So this was like a hour-long bug for me. Yep, and then you just do some range sums to count how many things are okay, and that's your answer. All right, that's problem E. So it looks like I passed system tests, got a negative delta. That's fine. We'll learn it back in the future. We got it. I'll probably absolve D if I get a chance today. But yeah, awesome. Well, thank you guys for watching. Sorry I don't have solutions to the second half of the set, but hopefully I guess this was at least somewhat helpful. Have a great day. Hope you had a great contest, and welcome to 2022.